Okay, let's start. Firstly, those of you who couldn't attend yesterday's review, I posted the video and I also posted the both kind of the original slide set and also slides with my scribbles on it. So everything should be downloadable. Um, uh, if you have any questions, just shoot them on Piazza. Generally speaking, I would really like to urge not to send private emails to TA or to me, because then the problem is that not everyone benefits from it. And generally speaking, the only response you will get back from us is send on Piazza. So might as well just send on Piazza. So just I want to avoid kind of direct thing that not everyone can benefit from. So yeah, just make use of that. Also, as you go around preparing for the midterm, if like you feel free to discuss solutions to the questions I presented yesterday. I kind of walked through the approach there. I didn't give the answers. There was a request to present the answers. I'll try to do it tonight. But the questions are fairly simple, so you should basically be able to do it, and feel free to share among yourself. So what I wanted to do is sort of go over the Bluetooth, partly because almost all projects are going to need it, and I had circulated a little write-up that Ji Han, who's serving as kind of an informal TA, an additional informal TA for the course, has prepared, and I'm going to walk through that, and it's just kind of a scaffolding on which you can kind of build things up. But before that, to be able to appreciate and understand, you do need to know what happens in Bluetooth. And in particular, we are using a part of Bluetooth which is called Bluetooth Low Energy, and I had started down this last time. But for the sake of completeness, because it has been quite a number of days since I presented this, so I'm going to kind of go from scratch on this one. So BLE kind of came number of years after Bluetooth actually sort of started. And this was basically driven by the fact that original Bluetooth, which was kind of meant for like headphones and microphones and serial devices, it was kind of a wire replacement kind of a mindset. Variety of reasons didn't catch on that much, but biggest part was Apple didn't support it because they required a very expensive crypto chip behind it. And the reason I think Apple partly didn't support it was because it was a pretty energy hog. You couldn't have a sensor which you are just passing by and immediately connect to it. You had to spend several seconds for a connection to be established before anything could be done. So while original Bluetooth was quite neat, but it had limitations. And meanwhile, because of competition from some proprietary standards such as ANT, which I had presented in the previous lecture slide, which was gaining traction in health market, so like sort of wearable sensors of various type, which would hook up with your exercise machines and all, they were kind of gaining some traction, including being built into some phones, and including actually some support from Apple also. So Apple for a while with Nike had these shoe sensors, which you could put them on your shoes and they would last for months, and they would count number of steps and stuff like that and all. And that had an ANT radio, and of course, therefore, so did the iPhone, but it was never advertised as such. Sony phones used to have ANT radio as well. So BLE kind of came out as a reaction to that, and it's meant for applications where you are transferring very small amounts of data relatively less frequently. So it's not intended for let's create a permanent connection, and designed for therefore lower data rates, lower power. That's what was happening, and therefore the power consumption, the transmit power rates were kept to be quite low, and therefore the distances which it was usually meant for was 2 to 5 meters. So that's what you kind of see out here. Sorry. So this is kind of the operating thing. So these are radios which were optimized for short range, low power, and would sleep a lot. So nowadays, BLE is of interest primarily because if you create something using BLE, it pretty much works for every device you can imagine: Android phones, iPhones, laptops, your cars, and so on and so forth, exercise machines. So the two key concepts out here, client and server. And server is the peripheral. It's a sensor server. So your Hexaware is a server. So this is where Hexaware goes, for example. And then you have the client, which is usually your phone, but it could also be a device like Raspberry Pi. And then there are things which can act as both. So usually your phone or Raspberry Pi can actually also act as a peripheral in some contexts. So the first thing BLE made use of is what used to be packets in the original Bluetooth meant for advertising the presence of a device. So originally in Bluetooth, there were these packets that a device would send out, basically saying, hey, I'm here, hey, I'm here. And then that was used as the initial hello to then pair up with kind of a bigger computer, and then you would create a connection and things would go off from there. So what BTLE kind of did was they kind of make use of those advertisement packets, but now they also carry data. So the idea is that the peripheral, the server, broadcasts its presence by sending out these advertisement packets, and then the client periodically goes into a scanning mode and which basically is listening for advertisement packets, and then the advertisement interval is what affects latency and power, right? I mean, so this thing basically ends up affecting latency and power, or rather average power, right? So you would see that these things can range from like kilohertz type rates all the way to fraction of a hertz. Okay, so that's a primary mode of thing, and it turns out that we'll see in BTLE that this thing carry 31 bytes of data. So very limited. These are small packets, but you can put in some amount of data out there, and I'll describe how things happen specifically in Hexaware. Now, for a variety of reasons, which we discussed the last time we had this lecture, if you had a single channel, then it's possible that that channel may have interference. Partly, we had talked about that how microwave ovens operate in that regime. You have Wi-Fi. So there are a variety of sources of interference. And since it's actually an open band, a so-called ISM band, there are a whole bunch of devices, baby monitors, and sort of all sort of other gizmos that have appeared, which operate in that in that part of the frequency. So Bluetooth take several measures. So firstly, this notion of a channel itself is kind of a tricky one in Bluetooth because it's actually a sequence of frequencies it hops over. Okay, but ignoring that for the moment, it also transmits things on multiple channels. So the idea is even if one thing is compromised, a different channel you could go through. So the observer, the phone, would scan on one channel for a while, and then scan on another channel for a while, and so on and so forth. And then meanwhile, the broadcaster will advertise potentially on multiple channels. There are 3 advertisement channels. And then the advertisement interval dictates when the advertisement restarts. So this way you are hedging the bet and making things more robust. Now, it turns out that 31 bytes may not be enough. So if all I could do is transmit in that advertisement, and that advertisement also has some other information like the MAC address, like the identity of the device and all. But even then, 31 bytes is not enough, and you could send changing data over it, but you can't really do much sort of much serious communication over that. So there are a couple of additional things that BTLE protocol provides for. One is that you can create a connection. And the idea is you can think of a connection as a short sequence of message exchanges, and then you tear down the connection, and then again that connection recurs later on. So it's not like permanent, but it itself occurs with a certain frequency. Okay, so just like the advertisement packets duty cycle, similarly the connection will have a duration and a period of occurrence. And in that connection, packets can go back and forth. So this is the only way if the observer wishes to send something to the broadcaster, that there has to be a connection. And the kind of things you might want to send over are things to configure the device. So like, for example, maybe you want to tell the broadcaster, change your advertisement interval. Okay, so even that information would go there this way. But more typically, it could be things like blink the LED, move the whatever, do some actuation, stuff like that. So all of that can get done using this connection request and a subsequent sort of exchange of packets that goes on. So you set up a connection, and then once the connection is set up, then you have exchange of packets within the connection, and then there is a connection interval associated with it. So the connection itself has therefore parameters. It's not like forever. You have a finite duration for a connection, and then a frequency or whatever interval with which the connection occurs. So that's one part of it. Another one, which I guess this slide set, this particular sequence of slides didn't show, is the following: that after this, after a successful reception of an advertisement, the observer, one of the observers, because there will be many observers, right? They're all listening to this advertisement. One of the observers can ask for an additional packet, in which case it will make what is called as a response request, and then the peripheral, the server, can respond. So actually you have potential for a follow-on packet also to the advertisement, and that one is another 31 bytes. So you can actually send up to 62 bytes independent of a connection. The only thing is these 62 bytes only go one way. Okay, there is no backflow of information. So if you're happy with 62 bytes of the sporadic information going, you don't need to do connection establishment. Now, a challenge with other things associated with, so plus 31 byte of follow-up. But the challenge with all of this thing is this is all open. That is no crypto and heard by everyone. So which is good and bad. Firstly, everyone can hear it. So if a sensor here sends out something, all your phones can listen to it. No encryption needed, no pairing needed, nothing. But one-way traffic, and it's kind of low bandwidth, right? It's 62 bytes max, 31 bytes typically, with some duty cycle rate once a second or something like that. So it's meant for really low rate stuff. But it works great for example, you might imagine you walk into this room and there is the light switch here advertises present. Hey, I'm here. I'm a light switch. I control the light in front of the room. So those kind of information could be there. It's used very successfully by things like tags on luggage and stuff like that, where basically what happens is in that 31 byte sequence, they carry a UUID, okay? Unique universal identifier, okay? So essentially kind of a long bit string sufficient to uniquely identify that particular tag, and then you're going to take that UUID and then consult some database and then find more details about it. So like the UUID might correspond to a particular product. So when you are standing near that product, it's transmitting its UUID because it has a Bluetooth transmitter, and then your phone picks up, your phone sees the UUID, it consults the database, says, aha, I'm standing near whatever, an Arrow shirt, and then all the details pop up on your phone corresponding to that. There are other advantages of things like this that senses one-way traffic. So you are not telling the sensor about yourself, right? Your phone is not transmitting anything to the sensors. Your phone is just listening to the sensors. So from a privacy perspective, there are some advantages also. Whereas the moment you establish connection and you are sending something, then of course you're giving up privacy. So if you're just snooping on the world, kind of these physical objects which are advertising itself, advertisements work great. Apple uses it for something called iBeacons, and then Google a little bit later followed on with something called, I forget the name, Eddystone. Yeah, Eddystone is what Google calls it. And they both work in the same concept that those 31 bytes carry a unique identifier, kind of like a URL, if you may, which basically lets you get information. So that's some of the basic jargon. Then what is happening is that, so you see there are two modes. There is this advertisement mode, and then there is this connection mode. So in the advertisement mode, the device is advertising, and any number of observers may be listening, depending upon when they're scanning. And there is no authentication, nothing out here. So no authentication, no encryption, okay, but unidirectional. The other mode is the one where you establish a connection. And in that case, a peripheral can take part in only one connection.
When you say no authentication, does that mean so like for an observer to kind of read that connection, but
I think the observer just has to listen.
still listen, so does it still need like the UUID of the broadcaster?
No. So all that will happen is in the broadcast, the content would have some information, and then the app running on the observer would interpret that. And what happens is that in case of iBeacons, for example, part of that 31 byte is reserved for what is called as a manufacturer field. So Apple says this is an iBeacon, and then remaining bytes are used to convey this UUID, which is a set of bits which are treated as kind of like a URL. That's one way of thinking about it. And then the idea is that the application looks at that and says, what does this UUID correspond to? And that would be within the application knowledge. So there's no authentication in the sense that anyone can read it. There's nothing preventing you from doing that. And in fact, you can pretty easily write programs on your laptop in Raspberry Pi to really just scan things around it. In fact, there are some apps both on Android and iPhone which basically kind of, you fire them up, they basically just scan the space around you and tell you what are all the Bluetooth nodes around you which are advertising themselves. Okay, and some of them will maybe iBeacon, some of them may be Google Eddystone, some of them may be just arbitrary things, because the standard doesn't say what those 31 bytes are carrying. Okay, it's basically arbitrary payload at that stage.
So the UUID, does the observer or the central, it has to update the table, right?
Yeah, so I'll give you an example, like how it works. Okay, so there was a while when I had put iBeacons everywhere, wherever my life took me routinely. Okay, my office had it, my car had it, nooks and crannies of my home had it. Okay, and I was trying to track my micro mobility. And then what I had done was I had given each one of those tags a unique UUID, which they would transmit, and I could configure it because I purchased them where I could kind of set them up to be something. And then they would transmit. I had an app running on my phone, rather a student of mine wrote it, and that would send it to Google Cloud. There, I had a spreadsheet where I had UUID this is sitting in whatever near my whatever lamp next to my bed, so on and so forth. And then that would configure that, oh, I was near there. Okay, so it basically kind of you create that. Or to give you another setting, if you're, let's say, Macy's, then your app will know certain UUIDs, and whenever it sees that UUID, it will consult a database, which will presumably correspond to some barcode for a product. Okay. So it's really left to your discretion. That UUID is 128 bits or something like that. You can Google. It's a pretty long one that it's sufficient to uniquely identify every unique thing in the universe, like lots of bits. Okay. So the write mode is when you actually have a connection. And in this connection, the peripheral type devices can only engage in one connection. So they can be connected to one central device, but the central devices, like your phones and Raspberry Pis, are pretty powerful. They can simultaneously be in multiple connections, but with obviously different tags. So they can be hooked up to multiple sensors simultaneously and exchanging data with them. Once you have the connection, you can do bidirectional exchanges. And we'll see that what actually happens over these connections in a little bit. Moreover, these things can be authenticated. Okay, so you may not you may want some secret attributes here. You may want something which is writable. So you don't want someone coming in and controlling your light switch, for example. So in which case you might say that I want to make that protected. Only those who are paired with it should be able to do it. So this thing can be authenticated. Can be authenticated. Okay, with basically meaning pairing. And almost always you would see that devices that allow writing will require authentication because you have the ability to mess with stuff there. So things to note, the raw data rate is 1 megabit per second, but by the time you take into account that there is all sort of overhead bytes which go into preambles of packets and all, as well as your duty cycling, and these advertisements have certain rates and all, the actual data rates are closer to 5, 10 kilobyte per second, so that's more like 40, 50 kilobit per second. So you're operating at maybe like 5% efficiency of the peak. Okay, so so real bandwidth or real rate closer to 5 to 10 kilobyte per second. Okay, so rest goes into all sort of overhead and all. The other thing is the BLE radios were designed with rapid duty cycling and those kind of things in mind. So unlike so it's designed for sort of power manageability. Now to make all this magic happen, BLE leveraged something that Bluetooth always had called generic access profile. So Bluetooth was organized. Yeah, go ahead.
The previous, the top of the architecture of the second, the central connection.
Oh, that one?
So does it have any, like, because it's like, does it have any sort, because it is paired properly, like you have proper overhead actually for setting up the connection, is it well secure as compared to the other one, or
Compared to this, you mean?
Yeah.
Is it like more secure or what?
Yeah, more secure.
Yeah, not well. Firstly, it's more secure because you are only allowing certain entities who are paired to be able to communicate, to be able to read and write. But that part is also more efficient. So because, like you said, you have gone through the pain of establishing the connection, you can send more packets, and moreover, you can send more packets back to back immediately, right? I mean, so you can do a higher rate communication.
But they are not end-to-end encrypted.
Well, this is a single hop anyway. So it's the encryption here is link level, a single hop level. If you need end-to-end encryption, then this guy would need to have some mechanism to have a key with whatever your other party is, let's say some cloud service. Okay, you can have applications do it. In fact, some of them do, but that's outside the purview of this particular standard because this is just focused on a single hop. Okay, so you can do it, but you don't do it, and in fact, one of the challenges in this is the following, that the pairing happens between a device or whatever, between two pairs of devices and not between an app and the sensor. So that's a very important point. The pairing is between your phone and a sensor, not between the Fitbit app and the sensor. Okay, and therefore once the pairing happens, any data going from here is readable by any app on that device. And the only way to combat that would be to do some end-to-end encryption, but that is outside the scope of the standard itself. You can choose to do it at the application level. Like, for example, Fitbit may say heart rate will always be encrypted using a secret key which only Fitbit knows, and it will just ship it all the way to the cloud, and then it will be deciphered there. In which case, other apps on the phone would be able to see the encrypted data stream, but they will not be able to make sense out of that. But Bluetooth doesn't take responsibility of that. And the way the pairing is done again is the pairing is between a device and a sensor, and not between an app on the device and the sensor. Okay, subtle point, but very important because it points to a bit of a weakness in this architecture because your app, if the sensor data is not being encrypted other than over the link, then once one app can see it, then any other app can see it also. Okay, so yeah, the channel part I had already kind of described, so I'm skipping that. Okay, so Bluetooth always had this generic access profile, which is what it used to use for kind of devices to advertise itself and all, and basically BLE kind of made use of the same stuff for some data transmission also. So yeah, so device roles, I already talked about it. So what this gap allows for is advertisement and then also something called scan response. Okay, so there are two ways to send the data. In the previous figures, I only had the advertisement data payload, but there is a subsequent packet exchange that you can also do, and which looks like, as shown in this slide, that the peripheral is sending the advertisement data, and then at some stage, the central, the observer, can, having heard the advertisement, would send a scan response request, and then the peripheral will follow with a scan response data. So you can actually have up to 2 pieces of data. Now, the particular Python package that we are using, there are others, but the one which we have tried, called BluePy, when you ask it to do a scan and send a response, it actually sends both this and this, all the 61 bytes, okay, in one go. So, but even though under the hood there are 2 separate things going on, and I guess unless we have missed it, there may be some other way of doing where you can choose not to do the scan response. You can basically just do the first part and not do the second part. That's really the prerogative of the central. So, but again, the particular package we are using, it does both on its behalf. So, having heard an advertisement, it will send out a scan response request, and any further response that comes, it kind of gives you the collective response for the two. So there is therefore up to 61 bytes of data can come through. Very important. Scan response request is just a dump packet. It has no content in it. No content as in you are not able to send any information back this way. There is no customizable information out there. It's basically saying, do you have a second packet to send me? That's all it is doing. Okay. So no app data in it. So main message therefore is that these 2 packets together still constitute a one-way traffic. You could set the rate at which you are advertising. So anywhere from milliseconds to seconds. So it's a fairly wide range. So you can go to like kilohertz to whatever, hundreds of hertz to order of a tenth of a hertz. These numbers may have changed from since then. This is part of the standard. It kind of keep revising based upon how the technology is changing, and this scan response request is, like I said, is optional. But even though the BluePy package we are using automatically seems to do it. Okay, so so while there is ability to now also establish a connection, a sensor doesn't have to do it. A lot of simple sensors just rely on this advertisement or advertisement plus the response to the scan. But you can also have connections. But for example, Apple's iBeacon, they just rely on advertisement. Okay, in the sense for their basic functionality, that's all they need. So basically what it does is it inserts a custom payload in the main advertisement packet, and that includes some UUID and all. Having said that, almost most iBeacon hardware that is made, they will allow for a connection to be established so that from an app you can configure those iBeacons. You can tell them this is your UUID. You can tell them transmit at this power. You can tell them transmit at this rate. But you could also imagine that iBeacons are being made in a custom manner where they're just fixed and they can never be configured. So there is nothing in the standard which kind of prevents that, nothing in the iBeacon standard. I'm referring to iBeacon because this was probably the first massive application of BLE that had happened and kind of got inserted in the commercial space quite a bit. So we have seen this picture, so I'm going to go past that. So now what happens once the connection is established? So when the connection is established, at that point, a different profile of Bluetooth gets used, and which is called generic attribute profile. And to kind of give you an executive summary of this, what happens is that your sensors or whatever these peripheral devices, you can think of them like a table of attributes or characteristics as they are called. Those characteristics have names which are hierarchical names. Okay, so it's like A slash B. Okay, so they're bundled into groups, and within groups there are characteristics, or you can think of them like objects with fields. Some of those characteristics are read-only, and some of them are read and write. So, like for example, heart rate may be a read-only thing, whereas sampling rate would be a write thing. Okay, so there are attributes of both types that kind of exist, and that's why it's called generic attribute profile. It's a profile meant for exposing a set of attributes. Okay, and again, the other name for attributes is characteristics. So it defines the way between how sort of the data is exchanged. It's not arbitrary data exchange. It's really reading and writing of these attributes. Okay, that's what's happening over the connection. So once a connection is established, we switch to this GATT, and in this case, we make use of this attribute protocol. And the basic idea is that these attributes really are thought of as bundles that are called services, and within services there are characteristics. So you can think of service as the container and characteristic as those attributes. Okay, and they're organized as kind of like a lookup table with IDs for each entry in the table. Connections are exclusive. So a peripheral is engaged in a connection with a single device. So this data is one-to-one transmission. So basically for that duration, of course, that cannot advertise itself. So stop advertising during the duration of the connection. And this is the only way to do the two-way communication. So that's another part. So if you want to write something to the device, this is the only way to kind of do this. Okay, so yeah, go ahead.
So if you only have one central for each peripheral, right?
But you can have multiple peripheral to a central.
Yeah. So in our case, if we have multiple, like for example, Xe was the Raspberry Pi, would the Raspberry Pi be like cycle to the different?
Yeah. So then it becomes the details. Since obviously there is one radio, so at any given point in time there will be only one active connection, right? But you can cycle through those connections, right? Yeah, but there is nothing prohibiting the standard from somehow kind of accommodating, like having multiple Bluetooth radios or whatnot, being able to do it. So one very important point to remember is two peripherals can't talk to each other. Okay, so two hexawares can't talk to each other, not using BLE radios, because it's only capable of a peripheral mode only. So if two peripherals need to talk to each other, let's say they want to synchronize their clocks or send data to each other, they have to do through the central device. Okay, central device has to coordinate between the two. Again, once the connection is there, you can exchange data in two ways. Yeah.
It's only half duplex, right? It's not.
Yeah, all radios are half duplex, unless they are deliberately designed to have a transmitter and a receiver operating in different frequencies, which is relatively rare. Okay, so I won't say they never do, but it's relatively rare. And the other thing I would say is that some recent work in the past 3-4 years, ironically in computer science, not in EE, has figured out clever ways to make ordinary radios act as full duplex radios. Okay, they do some fancy computation on top to kind of make that happen. Essentially what's happening is you're transmitting and you're also receiving something, right? And what you're transmitting, you hear it very loud. This point I had made sort of a couple of times already, right? Well, it's not an echo, right? I mean, if I'm sending to you, then of course my ear are also hearing what I'm speaking, right? Okay, in that sense. Except I know what I'm speaking. My brain knows what it is speaking, and therefore it can subtract it, right? But it needs some fancy timing details and all to be worked out. But since whatever. The processor knows what was being sent out, therefore it could subtract it, and that's why I meant that by computational tricks and all. Because otherwise, basic challenge is that what you are hearing your own transmission very loud, and it swamps out the incoming thing. So the orthodoxy was that it's very hard to have full duplex radios, but starting around 4 or 5 years ago, a group at Stanford and a group at Rice kind of jumped onto this problem and showed that it's practical to create these things. Okay, so they exist, but the computing needed and some of the antennas needed are tricky enough that you don't find them in our ordinary radios, but it's doable. Okay, but shorter answer, the radios you encounter, Bluetooth et al, are half duplex. Namely, they can either transmit or receive at any given time. Okay, so what's happening is that the peripheral has a table, which is a table of attributes organized in terms of these services and characteristics. And I'm going to talk about what those services and characteristics look like. And then the client basically sends a read request or a write request. So it's basically saying, read this attribute and send back the value, or write to the attribute and here is the value. So that's basically the protocol over the connection. You can't do anything else arbitrary. Anything you wish to do has to be organized in terms of these attributes. Additionally, there is associated with the connection, there is a connection interval. So the idea is that every connection interval, the central device will try to reconnect. Okay, so this is kind of an agreement. Like the first, after we have negotiated the connection, we'll say, every 10 seconds I'm going to contact you again, so that the sensor wakes up. Okay, so this is because you don't want the sensor to be up waiting for the connection request, right? So you want to duty cycle in terms of these also. So you set up a schedule in advance that every 10 seconds or every 5 minutes or whatever we are going to do it, we are going to contact, and then the sensor will wake up in time for that. So this connection request is really just a suggestion, and it is possible that during that time the central device is busy doing something else, and therefore the actual communication may not take place, and then you will do it the next time. Okay, so essentially, more precisely, therefore, things are that central tells the peripheral that I'm going to contact you every 10 seconds, and every 10 seconds the sensor will wake up, see if the central is there. If not, go back to sleep. Okay. Now, having said that, I have seen some references which indicate that the suggestion as to what the connection interval is comes from the central and not the peripheral. I don't know which one is true, but I believe it is the peripheral because that is the battery constrained device. So it's the one that proposes, and things go from there. But I'm not entirely confident on this statement out here, but I'll follow up. I'm kind of looking through some other sources also. Okay, so what happens then is during the connection, the client, namely your phone or Raspberry Pi, basically is going to send a request, which would be a request to read or write an attribute, or more precisely a characteristic, and then the slave will respond to that. Okay. So now more about these attributes. So the attributes are organized in terms of these services and characteristics. And in turn, there's a higher level concept called profile. So profile is a bundle of services that a standard has defined. A profile, and I'll show you some example, a profile is made up of certain services, and each service consists of a bunch of characteristics. So it's basically, you can say, it's kind of like a hierarchical naming of attributes, hierarchically organized attributes or characteristics. So for example, I may have, the standard does have something called a heart rate profile. Okay, so the heart rate profile, as the name you might imagine, is meant for products which are seeking to provide heart rate functionality. This profile is just a definition. There is no such piece of software or data structure called profile anywhere. Okay, it's just a definition. It's a definition of a collection of services which are defined by the Bluetooth standard. And the idea is that products which seek to provide similar functionality can all claim to follow a particular profile so that an app can talk to any heart rate sensor, for example. The profile in turn consists of two services in this case, a heart rate service and a device information service. So one is kind of the core service and the other one is providing some metadata out there. Okay, so profile in case of the heart rate profile consists of two services. So now when we are talking about services, now we are beginning to talk about actual data. Okay, service was profile was just a definition. So services is how we are breaking up the data in the heart rate profile into some logically meaningful containers. Each one of them has a unique numeric ID, which could either be 16-bit for some standard defined services or could be 128-bit for custom services. And 128-bit is when it is a UUID. So for example, heart rate service, so remember the heart rate profile had two services. There was a heart rate service and then there is a unique device, whatever, device information service. The heart rate service has a 16-bit ID of 180D because it's defined in the standard. And it consists of three characteristics. The three characteristics are the heart rate measurement, which is mandatory, and then two optional ones, body sensor location, where the sensor is located, and a heart rate control point, whose meaning I don't know, but that again has something to do with controlling something, and that too is optional. So characteristics are now kind of like variables, okay? They encapsulate a single data point, but they may consist of arrays of related data. So for example, many sensors come with multiple channels in them, like accelerometer and gyroscope and all usually have 2 or 3 channels in them corresponding to 2 spatial or 3 spatial dimensions. So there could be arrays or tuples, however you might want to look at. These two have UIDs or corresponding to them, which again can be 16-bit for the ones which the standard define, or 128-bit if you choose to define one yourself. Now 128-bit UUID, 128-bit is 16 bytes. Okay, so that's a fair bit of UID, a fair bit of your payload going into the stuff, but you get to define your own custom things. So you could have standard characteristics, in which case you save space, but you have to comply with what the standard is defining, or you can have these custom ones. So for example, the heart rate measurement has a UID of 2837 because it's defined by the standard. Then it has an 8-bit value describing the data format, whether that data format is an 8-bit integer or a 16-bit integer or something else. It's like the data type. And then finally, there is the actual heart rate measurement bytes in the particular format that exists. So a sensor may advertise itself, I have the heart rate measurement characteristic. It is a 32-bit float, or okay, let's stick with it. It's a 32-bit int, and then it will present the 4 bytes for it. So you can see that the standard is defined to be fairly flexible. You can kind of, the data types and all are all kind of controllable by you. Okay. So that's the notion of characteristics. This is how you also send data back to the peripheral. So for example, a UART type interface may provide a couple of characteristics, transmit and receive. One would be read only, another would be write only. So let's say your peripheral, for example, had a UART through which it was talking to something else. You may expose, the peripheral may expose that UART via a UART service, which has these two attributes, one for the transmitter, one for the receiver. So it's pretty flexible. You can do sort of a whole bunch of stuff. Now, again, all of this is just part of the standard. That doesn't mean that any given specific device is supporting any particular attribute. That depends upon the device itself. So therefore, that's the picture that we have. Peripheral would have services. Services would have characteristics. Some of them would be read. Some of them might be writable. So this is a further example that there is a heart rate the monitor service within which is heart rate measurement and body sensor location, and then for each one of these characteristics you have the value and a whole bunch of kind of other stuff that may be defined for it. So over the air, then what goes on, if we kind of zoom into this thing a little bit, okay. So I have frames or kind of the packets which are going through. They have preamble, access address, this is just part of all the Bluetooth frames, and then there is a protocol data unit, and then at the end there is some CRC. And advertisement channel payload looks like this. It has a 2-byte header and it has a 38-byte payload. In that 38-byte payload, there are various types of advertisement payload and scanner request and some other things. For us, what matters is advertisement payload. And within that, again, some bytes are already taken up. So the user definable bytes are 31. And then you have the data channel PDU, which again is defined in terms of these things. The point I want to make is that the actual payload, by the time you take into account all these overheads, like let's say you are sending 1 byte of sensor data, okay? You are paying 5 plus 3, 8 bytes at the frame level. You're paying 2 bytes of header, so that's 10 bytes, and then you're paying some additional bytes out here just to send that 1 byte of data. So it's the throughput can be actually quite low in this process. So shortest packet is 80 bits, longest packet is 376 bits. Okay, so those are just details. Yeah.
So we said that BLE, you just have like 31 bytes or max 62 like different packets, but over the airframe supports up to 37 bytes.
So over the airframes is 1 plus 4 plus 3, so that's 8 plus.
But the payload part itself, right? Just kind of the header supports from 0 to 37 bytes, right? Does that mean you could potentially put in more than 31 bytes?
No, some of them I believe are already taken up by some standard fields. That's why you're not getting them. Yeah, I'll get back to you on that detail, what those other fields are. This figure doesn't show that. Yeah. So, but at the end of the day, the magical number that would matter to you is 31 bytes is all that can be sent. Actually, on Hexaware, your choices are even more constrained. So I'm going to describe that also a little bit. Okay. Okay. So devices that you find out there now, you will hear them being so-called single mode and dual mode devices. And this thing kind of talks a little bit about that. So basically, there is a classic Bluetooth, the one which historically existed, where you will do the pairing for doing anything. There is no advertisement mode type data exchange and all. You will establish a connection based upon pairing and all, and that is called Bluetooth DR/EDR. EDR stands for extended data rate, so it can go fast. Okay, you hear about how Bluetooth 4 and all have 2 megabit per second type data rates, and all to get that you have to essentially get into this thing. But one big disadvantage that it is not something which is freely supported, particularly if you want to create a sensor like this for Apple devices, you have to pay Apple a lot of money to be able to do it, and it's not very power friendly and latency friendly. Then you have BLE, and devices like Hexaware are BLE peripherals only, and then there are devices which could be BLE central only. But point is, many of them will only support BLE, nothing else. And then there are devices which support both. They are called dual mode because they're supporting kind of the classic Bluetooth and they are supporting the BLE. And your laptops and iPhones and all, they are kind of like that. They do support sort of both. Finally, new kid on the block, Bluetooth 5. It appeared in Samsung S8 first, and then iPhone 8, 10X, and that generation, and now presumably on a bunch of other phones as well. And what it began to do was it began to provide some additional modes as well. So as you can see that this is kind of a table. So one thing it introduced is it introduced data exchange where there is error correction also going on. And the idea is that with this error correction, you can go for longer range. So you see that there is a range multiplier sitting out there, and these two things supposedly have kind of a longer range, but at the cost of reduced data rate. Okay, the reason the data rate is reduced is because some of your bits are now going into encoding for robustness. So Bluetooth 5 introduces these extended range modes while compromising on the speed front. So again, it is required that any Bluetooth 5 device support the classic mode. So they are by definition Bluetooth 4 compatible, but then they can optionally support these modes. And then it has a higher data rate mode also, so sort of shorter range, higher data rate. So you could see classic, if the classic Bluetooth has a range of 1, then the extended one has longer ranges, and the higher speed one has a shorter range. Okay, so it kind of went in both directions there. In real life, obviously, things don't quite pan out the way you would think. So real life data throughput, I picked it up from some articles which kind of did measurements. So this is what kind of a standard numbers, but you see what you get in this. So the other thing I would also mention is that within Bluetooth 4, there have been 4.0, 4.1, 4.2. So there have been some changes in the standard along the way also. And also somewhere along the way, the terminology associated with BLE also changed because there were some trademark issues and stuff like that. So the jargon I have used, you might see slight differences, and there were also some subtle changes along the way. Most of the major changes had to do with that 4.0 had some coexistence problem with your cellular standard, LTE standard. So one of the things they did was to fix Bluetooth so that it would interfere less with LTE. That part shouldn't really matter to us at all, but I'm just presenting this in case on websites you see things somewhat at variance with this. That's it. It's very hard to kind of get it right. I don't even like knowing precisely whether a device is supporting 4.2 or 4.1 or 4.0. There's a lot of variation out there. So just bear in mind, at 5 you are unlikely to encounter because Hexavia doesn't have it, Raspberry Pi doesn't have it, but your phone may. The other thing 5 has done is it has provided, because BLE became so important, so as part of Bluetooth 5, they have provided a whole bunch of extensions to better support BLE type applications. Okay, so firstly, they added a whole bunch of new types of PDUs to support Bluetooth LE type operation mode. So for example, you could do multiple sets of advertisements, like you can advertise different things to different parties. You can do advertisement in a more sort of deterministic manner. There are a whole bunch of additional things that they introduced, including some additional advertisement channels. I'm not going to go into them, but just by the time this stuff is taught 2-3 years from now, anyone teaching BLE, it will probably be all Bluetooth 5, but right now it's still kind of in the future. It's supposed to be a huge growth area because lots of products are using BLE just because of its power characteristics. And there is also the idea, the kind of things people are envisioning and all is that kind of these beacons get built into the fabric of the physical space, so to say. So buildings may be built with these things, your light switches and all that, kind of all advertising itself. And as you're moving around, apps on your phone are kind of discovering what's around them and then kind of getting a rich experience, some amounts of media getting exchanged. So imagine being able to sort of walk into a room and then all the controls and all the conditions and all your phone becomes aware and then adapts to it, okay? And also lets you control things. So like, for example, you may visit my home and I may give visitors access to, let's say, turning on the light, for example. So through their phone with whatever your Google Assistant and the Alexas and these kind of things, you can control stuff. So all richer interfacing with the physical world. So on the Bluetooth 5 side, again, with that market in mind, they have larger packets. advertisement channels being done in better manner. You can have advertisement packets which can be chained. So instead of single advertisement packet, you can have a sequence that can carry larger amount of advertisement data, periodic advertisement, reducing contention, and also advertising which is high duty cycle, kind of more frequent. So there's a bunch of stuff which is coming coming our way. So large packets, Bluetooth 5 allows packets up to 255 bytes long, so significantly longer than this. Part of the reason they're able to do it is because they are also introducing that error control also. But the other thing they are also doing is they are also achieving it in part by offloading to multiple channels. So you can send simultaneously on multiple channels and in effect have larger packets going out. This is chaining. That is, I can basically create a linked list of advertisement packets and thereby send larger amounts of information. There is, yeah, I don't think this is important. Okay, so I'm going to skip these. So that's Bluetooth 5. Now what I want to do is to show you the code which corresponding to the example which she has done, just to kind of show you what is happening. But before that, one thing I wanted to do was to show what happens in the Hexaware. So in Hexaware, you have two processors, right? So there is kind of a main processor, which is the K64, and there is the other processor, which is KW40, and the Bluetooth radio is part of that. And there is software here, obviously, and there is software here also. This software is factory firmware, and you are not going to be writing anything to it. You can, but not through embed. You can set yourself up with the local compiler chain and write the code, and then upload it using a programmer. Okay, so and you'll have to set the switches on your programming board accordingly. So unless you really set out to do it, this is not something you're normally going to do it. I'm not going to prevent it, but we're not teaching you anything about this anyway. Okay. When you're writing embed code, you're really writing firmware for this. So this is what embed is for. Now, of course, you can write this also the traditional way. You don't have to use embed, but in the course we are using embed. These two things communicate using a serial link. From the data sheet, it seems that it can support both UART and I2C. So in theory, you can use either one of them. The entire Bluetooth protocol stack is sitting in this processor. So this thing has a Bluetooth stack, Bluetooth software stack, which was written by Hexaware as part of the factory firmware. By the way, your capacitive switches are also hooked up to this guy. So those 6 switches on the faceplate of Hexaware. All the other sensors are here. And the display. And the battery and all sort of other stuff. So the question then is, how do I talk to the Bluetooth? So what has happened is that the software on the right processor has exposed a very particular abstraction over the serial link. In particular, the abstraction is one of callbacks. That is, it is going to request something. So this guy at some times is going to request something, and then this guy will respond. So in particular, and now it's time to go to the code. Excuse me. Okay, so firstly, this if you look at the G's document, you would see that he points to this hexaware modified. So this is just his example. He keeps modifying it, so the one I have may be slightly obsolete, but nevertheless. And in particular, you see that we are linking into a library called KW40Z, which is really the the chip on the right hand side. It's a MCU in its own right, and you can browse through it to kind of see what kind of things it provides, but this is all written for you. We are not going to go through that, but it's instructive to see how it works, okay, but I'm not going to go through that. In our main, what I want to walk you through is the kind of functions. This is a sample application one is writing, okay. So first thing you see is that I am writing callbacks corresponding to different buttons. Because remember, the buttons are on that other processor, as I mentioned in that previous picture. It's actually handled by the same processor as the Bluetooth. So in this case, we are writing callbacks for right button, left button, and in this particular case. And then further down in the code, you would see how are they getting attached, okay. So let's go down out here. So let's walk to the main. So in the main, you see that the KW40 device is essentially object which is really referring to that MCU. In that, we are saying attach button left, so it exposes a method called attach button left, and to that we are passing a pointer to a function, okay, and that function does something. In our case, it has something to do with Bluetooth itself. So we are attaching that. There is also a method called passkey, and there is also a method called alert. Now this is where the way that designers of that factory firmware did, they basically gave the provision for a special alert characteristic. So whenever the phone accesses the alert characteristic, it's a custom characteristic, then your this particular callback gets called. Moreover, it's an authenticated one, so there is also the passkey stuff. And you would see back up here the passkey thing. It actually presents a pairing code, and then yes, no. So essentially what happens is when your phone tries to pair, on the phone application, you are going to show you'll have a passkey, and then that passkey will appear on the screen. So that's what is happening out here. This OLED.text box is basically going to pop up the string text which we wrote out here onto the screen. Okay, so this is also showing you how to write on the OLED screen of the hexaware. And then using the buttons, you are going to accept or deny. Okay, so essentially the pairing request comes from the Raspberry Pi or the phone, and on your hexaware, you are going to see the code and you can accept or decline. Okay, kind of like the way we do it here. So, but the main point, remember, is that these functions are things you are writing, but then you are attaching it via the methods that are being provided. Via the methods which are being provided by that abstraction. Let's see. Yeah. So there's some other stuff going on. The other thing is what happens when this alert comes. So alert, as I said, is a custom characteristic which will come when the Raspberry Pi tries to access it. So let's look at this function, attach alert. Alert received. So this is what you see. Alert received, again, does some stuff, but it basically toggles LEDs. Okay, so it's basically maintaining. Actually, what it does is alert received will have a string, and depending upon what the string is saying, it basically turns LED on or off. So let me show you the corresponding Python code, just so that you see what is going on there. So this is a very simple example, but gets the point across. So firstly, we are using some particular package called BluePy, but the main part of the code, let's see if I can, yeah, okay. So you see that there is a MAC address, and we'll let you guys figure out how to find out the MAC address for your Hexavere. Command turn on and off are the two commands that we have defined, and then what you see out here is that we open a peripheral, we connect to it using the MAC address for the Bluetooth, and then we get the characteristics corresponding to a particular, the one for the alert characteristic, so it has a UUID of 2031, and then we can write commands to it. So there are two commands we have defined, command turn on and off. You can define a whole bunch of them to be able to do it. When you are reading, G is going to hand out some examples for that also, but basically you're going to read from those characteristics. So what would be instructive for you is to go and read the manual man page for BluePy to see how you read and write characteristics. And now going back to how the other characteristics get handled, so you will see in this code that there are also examples for updating various kind of sensor data. So all the other characteristics are handled by that other processor. All you can do is you can tell the processor what the latest value of something are. So for example, I can send to that MCU battery level, ambient light level, humidity level. These are all methods defined by that guy. So we can just update it. So in this particular case, I have a task which is running continuously, and it keeps updating the values on the attribute side. And these are all defined because these are the sensors which are built into the Hexavere. And in this piece of code, actually, towards the end, the updated sensor data values are all fake. It's not actually reading any sensor, it's just inventing some numeric values and just increments them. But in a real system, you are going to read from the actual sensor and then push them out. So, so that's kind of the basic structure. The reason I'm pointing that out is what this means is that the only characteristic for which you have control over really is this alert characteristic, okay? At least what it appears to be from our investigation thus far. All the other characteristics are actually being handled by the other MCU, and you basically provided the data. You are not directly handling those characteristics. There is no callback being done to you when an attempt is made to read those characteristics. You are only putting in the data there, and then data gets out. Now, there is nothing which says that the sensor data has to reflect your sensor reading, right? I mean, you can put any fake data out there that you feel like. So you can certainly use these channels, these sensors for any other purpose also.
I'm not sure if I understand right. The Raspberry Pi or the phone, whatever, when it sends the alert, so that's when the communication between the two processors is.
No. The alert is just a custom characteristic.
Okay.
So that is a writable characteristic, and you send it a command. That command is what I showed in the thing, okay? And how that command, what to do on that command, a callback happens, and you are writing a function to do something. So that command will simply say whatever, turn on, write something on the display, whatever. Okay, you get to define it arbitrarily. All the other sensor readings are predefined characteristics in the firmware of that second MCU, and you are not directly involved in handling the response to that. All you are doing is you are telling the MCU this is the latest sensor reading, and you keep doing it whenever you feel like. Okay. And the other minor point I was making was that the value you provide to that other MCU doesn't need to reflect the actual sensor data. It could be any gibberish or any special thing that you do. So you could, for example, use the temperature data to convey number of times you have done printf. I'm just making it up, right? And what we have not shown you is the Python code to actually read those characteristics. We'll provide it, but you can figure it out yourself because you will see what characteristics are there. Yeah.
So the data is communicated either over I2C or UART.
Yeah, I mean, I don't know precisely which one they're actually using in the software there, but the hardware link is capable of supporting both. Yeah.
So what this essentially does is this MCU, the main MCU, reads all the data
the main MCU can read the data, right? I mean, in this fake code, we are not even doing that. We are making the temperature reading to just go from 200 to 4200. We are just counting it up. We are not even bothering to read the temperature data. Okay, and then what we are doing is we are just updating the sensor data at a particular rate. Okay.
And then it sends over to the.
You send it over. So that method that we are using is presumably using that underlying UART to send the data over. And you should be able to, by looking at the this one, the HEXI KW40 CPP, you can see what is going on under the hood there. Okay, but basically when I am doing that update, when we are doing this thing, send set application, send battery level, then it's resulting in whatever I'm passing going over that serial link to the other side, and then it puts it into that table so that when a device interrogates for the battery level characteristic, it will get that value.
So we're not creating custom characters.
Not for, yeah. So the only custom characteristic is the command one. So this is where the rigidity of the system comes in. You can't go ahead and say, hey, I want to define this new characteristic. So the only loophole they have provided is that one. Or alternatively, you can make use of existing characteristic for your own purpose. But they will continue to be called as the battery characteristic.
And these characteristics are exposed by the custom firmware model.
By the custom firmware.
And Mbed provides a way for us to access them.
No, so the only thing you can do is you can update the values behind those characteristics via these calls.
Yeah, I'm just correctly, but we can only make one custom characteristic, in which case this one.
You are not even making that. It's just provided for you.
Oh,
Okay, you are. So let me put it this way: you cannot make any new characteristics.
So
Okay.
whatever is existing, you just.
And that's all you can use because you cannot write the firmware on the other MCU unless you go to modifying it, right? So I'm going with the normal mode that you're just writing the embed code and you're not modifying that firmware. Okay, if you choose to modify that firmware, you can, but then you need a programmer to actually burn it in because it's no longer embed. You can, people are doing it, and if you decide for whatever reason that you want to do it, I have the programmer. I have a couple of those programmers, so you're welcome to use it. But it will not be through embed. You have to do it through a local compiler. It's doable, but if you can avoid it, avoid it.
So all we can do is to read from the characteristics that is already present. And
You cannot define any new characteristics. So from embed side, what you can do is two things. For the read characteristics, you can provide the data. But very important, you're providing the data asynchronously at some rate whenever you feel like, right? Not in response to a specific read request. Okay. And the second thing is that the one write characteristic, which is the alert characteristic, whenever a device sends a request to that, you get a callback, and then you can do whatever you want. Okay, it could even be that when that thing comes in, then you send in a new piece, put in a new data. I mean, you can create private protocols around it. So if you are creative enough, you can do all sort of stuff even in this constrained environment. To the extent possible, stay away from messing with the firmware on the other processor, because then you are going to open a can of worms, which is probably not worth it. Okay, so I just wanted to bring this part out because it gives you. So let me put it this way: every Bluetooth radio which is out there, they make the firmware pretty opaque. And the reason they do it is they don't want end users to be operating the radio in a non-FCC compliant mode, because you can use that radio and then mess with the frequency hopping in a manner which is no longer valid or no longer legal. So to prevent that, they make it super hard for you to mess with that. In fact, even when you modify the firmware on that other MCU, there's a part of it which is binary only. You don't even get to see what that source code is, because that's the part which actually does the low-level management of the radio. So the reason I'm bringing this out is there's a reason behind this madness. The reason behind this madness is that if they were to let you program that pretty easily, people will be operating things in a mode which no longer complies with the rules of the ISM band. So that's why kind of all this jump through hoops. So usually when you buy a Bluetooth radio, one which talks over a serial link and all, they have a little processor inside it, and all the protocol details are handled there, and all you get to see is some serial protocol. Okay, in fact, the standard even defines one way of doing it. Something analogous is basically happening out here also. Okay, so defining your own characteristics. Now, the reason I think an additional complexity which has happened out here is because of this split architecture. They have put the characteristics on the other processor. I think much nicer would have been if they had allowed us to define our own characteristics on this side also, but they don't. And I think uh, I'll see if anyone has bypassed that, but right now it's a fixed set of characteristics, one of which is writable, all the others are readable. You can update the data and you can do a callback for that write characteristics. So that's what's going on here. Let's see, how are we doing on time? Okay. We missed our break. You guys want a short break? Yeah, let's do it. Hi.
Can I ask you about our project really fast?
Sure.
So we're thinking of making a server again where two users have a Raspberry Pi and they come by each other, then they exchange information for and they can like interrupt each other for a short period of time before they leave it.
So again, so the Raspberry Pi users come with their.
So like, if you're users, they can be like strangers, and they come together. The Raspberry Pi will like alert them that there's another user in the Raspberry Pi in range, and our organizers were in range, and they can push the button, you can like download each other's information. It can be like a game where each user is assigned like a piece of a puzzle or a piece of an image, and when they come by each other, they exchange their own.
I like the underlying premise of the Raspberry Pi acting as a mediator in something that you are doing across these things. I think you need to flesh out a little bit precisely what you want to do there. But yeah, I like the premise. It could even be, you can even explore things like, something which required tight timing synchronization or things like that. That could be anything, or maybe something about location. There are some possibilities like that that you can explore. Yeah.
Something along those lines, like just
Yeah, but I like the basic premise. I don't think any of the other projects are going after this concept of Raspberry Pi acting as intermediate station or multiple things. You can even imagine, I don't know, like a game where who goes first or something like that. Or
XORs make a play
yeah. Okay. Yeah. Do something fun.
Just a quick question. If this star set, if okay, it's still static priority, so just try the hyperbolic bound. It's not
Just into
yeah, it's
So therefore now you have to go for the
higher, faster processor.
No, because remember that only shows that you still have to do the
How much?
no, either the theorem one based analysis or the response time based analysis to find out whether it is scalable. That formula only tells you one way, which is it is scalable.
No,
If it gives
if it's like 20 by 9, it's more than 2. So is
what is 20 by 9?
this multiplication? Okay, it's 4 by 3 into 5 by 4 into 4 by 3 again. So
Yeah.
it's more than 20. It's more
Yeah.
than 2.
So more than 2. So all it means is that from that formula it is not scalable. So it doesn't mean that it's not scalable.
At all.
Yeah, it does not mean that.
So we assign different priorities and see which.
Right. So which priority will you assign? Because it is rate monotonic, so you just assign the rate monotonic priority and then you do the response time test.
Okay.
Okay.
And then
only then you will know for sure.
for sure it's not.
Yeah.
So we just don't stop based on the U values.
Yeah.
Like
You stop only if it gives a positive answer. If it says schedulable, then you know it's schedulable, but not the other.
not the other way around.
Okay.
And then we decide how much slower. What is
Yeah.
the
So
upper bound you
okay.
can.
So for the how much slower part, you always have to do the response time analysis.
Yeah, because
There's
there's
no
no
choice.
other way. Unless we know that it's schedulable and we can push the limit.
Well,
even
the
if you push the
problem is the
limit,
following:
yeah.
if you begin to push the limit, again at
It
some
goes
point the
beyond.
formula will begin to fail, and you will have to do the main analysis.
Just one more quick question.
Yeah.
So this one, like this is straight away you have to apply the formula that the rate, the time, the response time analysis. So like giving priority to this based on the closest deadline 1, 2, 3 it fails.
Yeah, let's
So-
do it in the office.
yeah,
hour.
okay. Sorry.
Yeah. Want to move to the next topic in wireless, and before we wrap up wireless, basically, which is the low power angle. So for processors, we saw a fair bit of how we the kind of things which go on to make computing lower power. I wanted to do the same thing for wireless a little bit also. We saw a little bit intuitively, namely, of course, if you're not using the radio, shut it down. We also kind of talked about that if packets collide, then that's wasted effort. So that would be wastage of energy. But let's approach that thing a little bit more systematically. So to do that, one has to kind of understand a little bit about where does the power go in radio. Okay, I mean, before you can reduce it, kind of trying. So for processors, I had talked about power is proportional to what? V square F, right? The other terms in that thing have to do with capacitance in the circuit and all, okay? But V square F is the main thing. So that had told us that we can mess with the frequency, we can mess with the voltage, and we had talked about frequency scaling and voltage frequency scaling. What are the counterparts out here? Now, overriding all of this is, if something is not being used, you shut it down. So that applies to, needless to say, to any system, processor, radio, memory, sensors, whatnot. So let's look at the radio a little bit more. So what happens in a radio? So I had given a notional picture of a radio kind of 2 slide sets ago. I can coalesce all of that into something which looks like this. That there are really 3 pieces to a radio. There is electronics, which takes the packet coming from the processor and then does all that medium access control and modulation and stuff like that, all that stuff. And some of it is digital, some of it is analog, but at the end of it, I have a radio wave which I have to send out. But I can't just send it out because I have to send it out with adequate power so that the other party receives a signal of sufficient strength. So I will have an amplifier, an RF amplifier. This is going to boost things up. So like for example, when you hear this radio station is a 1 kilowatt radio station, what it's really referring to is that the signal coming out of that radio is being transmitted at a kilowatt. Okay, kilowatt is huge. Our Bluetooth radios and all are in milliwatts. Okay, so but when they refer to that, they're really referring to the power coming out of the antenna, and the signal from the electronics is boosted up to that power by this amplifier. And since this can consume a lot of power, so we are accounting for it separately. Then on the receive side, after going through this channel, potentially bouncing around obstacles or even going through obstacles like glass windows and all, the signal reaches out here. And by the time the signal reaches out here, then it induces some voltage and current in the antenna, very tiny. And then we do kind of the reverse path. We amplify it to boost up the signal, and then we process it through analog and digital. This channel has this path loss. And if you look at vacuum, then radio waves suffer through a path loss, which is 1 over d square. Right? This path loss. That's the electromagnetics, Maxwell's equations, which kind of tell us that. And this is only if there is nothing else in the universe, just those two antennas. But obviously there is other stuff. So in reality, the path loss is a lot more complicated. Just to in environment which are cluttered and where there are other obstacles, then we begin to model it as 1 over d to the power n, where n is something more than 2. So just for example, in a urban environment like this, n may be like 5 or 6 or something like that. If it involves going through materials, it may be something. If you place two antennas close to the ground, like imagine two devices sitting on the ground, it turns out radio waves reflect off the ground. Earth is a great reflector. So the d becomes more like d to the power 4. So real world is not 2, is a lot more. And in fact, there are lots of other terms, right? I mean, you may not even have a single path. You may have multiple radio waves bouncing and meeting at the antenna, and they may cancel each other out. That's why you have these fading when you're going under a bridge or into a tunnel and things like that. Okay, so there's a path loss. We have to make sure that the signal arrives here with sufficient power so that you can get good information out here. Low bit error rate. Now, what happens is that the relative balance of power between these three things becomes very important. So let's say I'm sending radio signal over a long distance. Then clearly, to meet my minimum requirement on the signal strength at the receive side, I'll have to send the signal at a very large power, and therefore my amplifier will consume a lot of power, right? If I'm sending over long distances. So long distance radios like cellular radio would be dominated by the power amplifier. They have to send stuff over miles. On the other hand, if I'm sending stuff over short distances, then d is tiny, so I'm less worried about this path loss, and then I'm going to get dominated by the electronics. Moreover, depending upon what your radios are, we have to worry about who dominates, transmit or receive. Now, if you think about it, transmits, what does a transmitter do? It takes the bits and it encodes them and it sends them out. Receiver, on the other hand, has a harder task because by the time the bits come out here, they have been corrupted. So receiver is not simply doing the undoing of what the encoding, that would have been straightforward. It has to undo and cope with all the errors which happened. So like, for example, what may happen is I transmitted something and it receives something close by. It has to find out what is the best match. So it has to do kind of a search algorithm there, optimization. So its job is much more complicated. So this is simple algorithm, simple computation. And this is complex computation. And in particular, if my channel is pretty bad, or if my data rates are high, or stuff like that, the job of the receiver becomes more complicated. So simple ways of sending information, transmit and receive may be comparable, but by the time you start looking at more complicated radio standards which are designed for higher data rate or bad channels, receive algorithms may be very complicated. So upshot of all of that boils down to is attempted to capture in this picture, which is if I'm looking at long range radios, amplifier dominates. That's the green color thing out here. And the other two parts are green. If I look at mid-range stuff, the picture begins to change. So firstly, in absolute terms, the amplifier power goes down. So if you notice, I've drawn these things in terms of nanojoules per bit. The leftmost curve goes up to 8,000. This one goes to 300, and the right one goes to 600. Okay, so they are much smaller. So the amplifier power goes down, and so the electronic power begins to be comparable. Now, still on the transmit side, it is green plus cyan. So in these pictures, it's still the case that transmit overall dominates the receive. The picture changes a little bit with Bluetooth, where green is even smaller, but still it appears to be true. But there are many regimes. This is kind of a generic picture. Many times Bluetooth radios and Zigbee radios can be in a range where the green plus cyan may be less than the blue. That is, transmitting is cheaper from a power perspective than receiving. Okay, and that gives you in a very different regime, because suddenly instead of worrying about I should transmit less, you have to worry about I should receive less. But even in these middle zones, you can see that receive is non-negligible. It's comparable by the time you hit Bluetooth. So you have to worry about receiving also. You can't. A lot of standards and a lot of traditional protocols were designed for this leftmost regime. The focus was minimize transmissions, and that is certainly true if I'm talking to something 5-10 miles away. But when you are in short range radios, you have to worry about the balance and perhaps even listen less. The other subtle point is whether you are actively receiving anything or not, the receive electronics will up. So just passively listening to see whether something is being transmitted is costly also.
So which means in all cases, okay, Wi-Fi and cellular have similar ETX and ERX.
That is not true, because the reason is the following, that as we are beginning to push data rates, the algorithms become more complicated. So you've got to realize also that LTE and Wi-Fi are now hitting data rates of hundreds of megabit per second, whereas your Bluetooth and these Z-Waves and these kind of things are still at megabit per second. Okay, so it's kind of a bit hard to compare along these lines. So I would be a bit hesitant to kind of draw that comparison, but the trends is what you can talk about.
Okay, but also one more thing is that Wi-Fi experiences. Okay, the distance of Wi-Fi is much more when compared to Bluetooth, so it is going to experience much more fade, and which means you have to put more power into the transmitter, and the receiver will also have a harder time recognizing the signal. So the number of nanojoules per bit for the transmitter and the receiver in Wi-Fi is much.
Yeah, so I guess you're saying why is this number lower here than on this side? Yeah. Okay, so the reason also has to do with the efficiencies of the modulation scheme and all that you are using. They are not the same out here. Okay, so we are using entirely different coding schemes and all. The radios are designed differently. They are using much simpler schemes, much less efficient. So, yeah. So don't go by the detailed numbers out here, because they are partly just meant to kind of illustrate something typical that I found at the time I drew these slides, which is 3-4 years ago at least. Okay, the bigger point I want to make out here is that receive can be tremendously expensive, and therefore in the regime that we are operating in with these embedded systems and all, you can't ignore receive. In fact, you need to optimize for receive, and in fact many a times your better strategy is to be profligate in transmitting and parsimonious in receive than in a left corner where it's really kind of the other way around. Okay, so what does that begin to mean for our power management strategies? So let's look at the sender. So at some level, sender is getting some packet from the host computer and has to now send it out over the antenna. And we really have this electronic component and the RF amplifier component, and then there's a total component. So if you think about the electronic component, the energy I will consume, the more time I take to transmit, I'll grow linearly, right? If I to the first order. On the other hand, the RF energy behaves a little bit differently. If I have more time to transmit, then I can transmit at a lower power. And the reason is the following, that from the receive side, what matters is the energy it is getting for a bit. So I'm sure all of you have heard the name Shannon at least. Some of you perhaps have even studied something about Shannon's capacity and all, but the very important metric for receiving is something called EB over N naught. So from a receive perspective, this is what matters. Apologies. Okay, so from a receive side, EB over N naught. EB refers to energy in the bit, and N naught refers to the noise level. It's basically saying that to successfully receive, EB over N naught should be high enough. So energy, so N naught is whatever the noise floor, so EB is what we care about. EB is energy per bit, so I can either have a short bit with high power, or I can have a long bit with lower power. So roughly speaking, therefore, if I have more time, I can transmit at lower power. And moreover, if I have more transmission time, it turns out there are some fancy modulation schemes I can begin to use that the energy begins to go down also. That is, if I use those schemes, then I can even lower down. You give me more time, I can do away with less energy per bit. In fact, computing works the same way. If I give you infinite computing time, you can do computing with zero power. There are asymptotically zero power. So doing things rapidly cause a lot of pain. So you have to trust this, because the reasons behind this is something that only digital comm courses provide. But for our purposes, what matters is that if I were to look in terms of time available to send data and the energy needed, and if I bring to bear all sort of tricks to this thing, the curve looks like this, that there is some sort of a distinct optimum point. If I transmit very rapidly, then I have to spend a lot of RF energy. And if I transmit super slowly, then the electronics will begin to kill me because it will have to stay longer. So there is kind of some sweet spot that I need to be operating in. What this also means is that long-range radios is where the RF dominates, right? That is where the amplifiers, so they tend to be kind of on this side of the story. A short-range radio would be somewhere out to the right. So that's what's happening at the sender. So if I begin to look at what things look like for different kind of radios. So unfortunately my legends didn't make it into the slide. So if you think about, if I have a long range radio, then it's going to be RF dominated, and therefore its optimum point would be way far out. So this is how a long range radio looks like, because it's dominated by RF. If on the other hand I have a short range radio, this is what it will look like, because the RF doesn't really matter that much. It's sending just stuff over the short range, and so it hits its optimum point very early, and then after that it's electronics killing you. So what it says is that for long range, your strategy is kind of slow is better to the first order, because the optimum point is way far out. And for short range, fast is better. You should send as soon as possible and then shut the thing down. So this is where shutdown is better. And this is where scaling is better. So what you would see is short range radios for Bluetooth and its types. Your best power strategy is send quickly, go to sleep, race to finish, okay? Whereas for long range radios, you play all sort of games to minimize, to come out here, to come to the right, okay? And that means use coding and fancy modulation and all those kind of things to kind of make things work out. So the way you think of low power in the world of cellular is very different than the way you think of low power for Bluetooth and short range things. And even at one level above, the additional constraint is that transmit is very expensive in cellular. So you try to minimize transmission. You try to minimize collision of packets, because every time you do a transmission and it fails to make through, you are paying energy for it. Whereas in things like Bluetooth, the mentality changes. Listening is expensive, and therefore, and it's okay perhaps occasionally to send a packet multiple times. So the name kind of, the things really kind of change from that perspective. So power management strategies are very different in these two regimes. So what that brings us is kind of much like processors, we have a shutdown strategy, and kind of the idea is that we transmit and shut down, and we again, when we need to transmit again, we sort of revive it. But what about the receive side? So there we have a challenge. The problem is that if the receiver has gone to sleep, how does the receiver know when to wake up? Right? In case of processor, what wakes up the processor? If you put the processor to sleep, what is it that wakes it up? An interrupt, like a user pressing the key or something coming in. In case of a radio receiver, what should wake it up?
The signal having some sort of preamble or something.
The radio is asleep, right? So some time, so it could be some sort of a time agreement.
That's like coding, right? Again, you lose energy in that.
Yes, so we'll see implications of it, but the problem is a tricky problem, right? I mean, you're putting to sleep, and the entity who has to wake me up is on the far away, so, and we need the radio link up to be able to receive that packet. So you either, so strategies include big dot little, namely I will have a little radio which is very optimized for wake up, and then it will wake up a big radio which will actually do the data transmission. Or we will do a time-based technique, mutually agree that we are going to speak on January 1st at precisely at midnight or whatever, those kind of schemes, something like that. Or maybe I'll create some fancier architecture for the radio where the main radio keeps sleep, and then we keep on the lookout for radio energy on the channel. And if there is, whenever we see radio energy, we wake things up and then attempt to decode. The problem with that is there is a lot of noise in the channel. So any microwave oven running can wake things up and all. So there would be some trickiness there. So it's actually a challenging problem. Processors have it easy because the wake up event happens locally. Here the wake up event Ideally, I want to wake up when the sender has something to send, but that's a non-solvable problem unless you figure out some way of communicating otherwise. Yeah.
The beacon packet inside the 802.11 is it periodic or is it like, I don't
802.11, the beacon packet is periodic.
or is it when the user has to
Well, okay, let me take it back. It is not precisely periodic, but it does operate at some rough periodic.
like is it when the user has to send some data, it wakes the receiver up?
Okay, so shutdown is the strategy number one, which is we put okay. So shutdown is the first strategy, and you basically at some point in time when you're finished transmitting, you go to sleep, and this will this will save on the electronic side. So this seems to make sense when electronics kind of dominate. The questions you come up with is when and how to wake up. Some of it we were discussing, and that is where you get into this separate radio, often called as wake-up radio or paging radio, or some sort of protocol based upon time, for example, or other options. We'll kind of talk about some of them next time we meet. And the idea is that after we are done transmitting, if we were to shut down, then whatever energy we accumulated, that's what we have spent. But if you don't shut down, then you will keep spending the electronics energy. Your RF part would be okay because it's not going to transmit anything, but no shutdown thing. So shutdown is one option. And next time when we'll talk about the second option, which is scaling, which is kind of equivalent to dynamic frequency or voltage frequency scaling. So we will talk about that on Tuesday when we meet. Okay.